Hey guys, good morning. Great energy, great conference up until now. It was great talk just right now. It's the first time for me to be in the Ukraine, so I'm really excited to have this talk today. So let's jump right in. 90% of the data that we have in the world today was created in the past 2 years. It means that it took us a few thousand years before that to get to merely 10% of the data. And we still keep accumulating more and more data in increasing pace every day. So my name is Shlomi, and I'm head of R&D at Wix Code. Wix, as you know, is a website building platform, and Wix Code is a rather new product built on top of that. We provide both backend functions and DB as a service. So we're actually building a cloud, providing a serverless environment for website builders with everything they need for running, maintaining, and scaling out their web apps. So basically, before that, I was an R&D manager at AppsFlyer. AppsFlyer is providing real-time analytics for mobile devices. And I was managing the real-time data flows group. We were processing billions of events on a daily basis in low latency. And Wix is a Scala shop. AppsFlyer is a Clojure shop, meaning 2 functional programming languages running on top of the JVM. And just before that, I had about 15 years of experience working in Java. During this talk today, I'm going to share my journey during the past few years, going through various event-driven platforms, handling the challenges of low latency event processing, and some of the insights I got through that journey. So our story begins with the fact that we need to handle lots of data. So a few years ago, I joined a small startup called AppsFlyer, and we started off with a rather simplistic architecture, looking a bit like that. You have a cloud of microservices in Amazon, AWS, microservices, ELBs, web servers, and a bunch of databases, basically communicating with one another in a synchronous way. So it's perfectly okay to start with a simplistic design and keep the evolutionary design from that, once you understand where your challenges are. And as I said before, fortunately enough for us, we were very successful. So we had more and more customers bringing more and more of their users to use our service. So the way it would reflect back to our monitors in the backend is a constant, ever-growing traffic that we need to handle with. In a single year, we grew from a bunch of millions of events per day to a few hundreds of millions of events per day, and a year after that to a few billions of events per day. And the sheer scale was the challenge that we needed to tackle. And I want to, as I said before, share the challenges that we saw. So reflecting back to that architecture, what will eventually happen, because we are working in under the paradigm that everything fails. So one of our services made some troubles. It can be due to a momentary increase in traffic, like a traffic spike, a hardware fault, or anything like that. And although there were a cluster of high available services, it was not enough to handle the increasing load. So by this current architecture, it will reflect back to service B and C as the customer of that service, and further upstream to the web servers, etc., which will basically brought us to a point when we have service failure, you have downtime, and basically even data loss. So that's not the way we want to continue. So we got back to the design board and thought, what about processing the data in batches. There's a lot of advantages to that. We started looking into tools like Hadoop and Spark and storing all the data in a data lake like S3. The advantages of that approach is that you can process large amount of data. You can spin up more and more machines in Amazon and run over a large scale of data, and you get great scalability. The major disadvantage of that approach is the fact that we are running in batch, like a job, nightly batch, or even every delta time, like a time interval. It means that you have an embedded latency. And although it is good, and we were working with those tools for data science and trends and aggregated reports, etc., we needed to come up with something else. The challenge that we see more and more in the previous years is the fact that more and more industries, more and more verticals need an actionable real-time decision-making. Verticals like ride sharing, healthcare monitoring, etc. You need to get your insights in real time. So what it basically means is that you need to come up with a real-time ability to process the streams of data. So the major difference between streams and batches that I came across is the fact that streams has a start, but it never ends. It's a constant data streaming into your services. So at that point, winter was coming for us, and we found ourselves back to the design board trying to think how would that reflect upon our architecture. So the next main thing was looking into queues and how we can benefit from that, processing our data. So as I said, back to the design board, we got back to basics and started looking into the Django 4 observer pattern. Now what will that give you is the decoupling of the observers and the data producer. So the data produced data, send it to a subject, and the subject will send the data to a collection of observables which are registered to that subject. If we will refer to the reactive manifesto, we can find that employing explicit message passing will enable us better management, elasticity, monitoring, and all that by the message queue. So what was very simple for us at that point of time was to configure Redis, which we were already using as a database, and it has a package for PubSub. So what it means is that if you have a data point that is updated, you can immediately notify a callback of that change. So you can configure multiple subscribers that will be notified of that change. So it's kind of a public subscribers paradigm that you can get basically for free if you're working against Redis. So what we gained is decoupling and parallelism. The fact that the different subscribers can work in parallel, get the same message, like different modules in our organization, different features, with, as I said, decoupling away from one another and from the data producer. So everything was really cool for a few months. And then I remember one night that it always happens at night in production, and we were fighting against that growth in production. One of our servers got into a limbo state, meaning it was up and running, so our monitoring did not catch up on it, but it was not able to retrieve any more messages coming in from Redis. So it just thought that there are no messages. Obviously, it was losing that data, and I remember that the manager of the company gave me a phone call in the middle of the night, shouting, saying that customers are not receiving the data, and we were not aware of that. So that's a really bad situation. And what we were still missing at that point is fault tolerant. I mean, once a subscriber is down, the messages are lost. Because the data is pushed to the subscribers. The subscribers are not saying, hey, I'm here up and running, give me the data. Okay, so we want to do that the other way around. And another thing that is not supported by this paradigm is concurrency. I mean, what if we want more and more subscribers of the same type? Not to work in parallel, but to split the load among themselves. Okay, so that's also going to be a challenge. At that point of time, again, we did some kind of a postmortem after that production issue, and we thought, how can we handle the messages better? And we thought, what are the virtues, or what exactly are we looking for when choosing an event-driven platform? So obviously you want the best performance, latency, it's the amount of time it takes the queue itself to process the data. You want to be able to handle very high throughput, number of messages per minute or whatever, and you want to be able to scale rather easily. You want to have good fault tolerant, means recover, like happened to us in case of a failure, and to prevent data loss. So for the consumer to keep from the exact same point it stopped. Queue is message ordering, first in, first out. That's what you would expect from a queue. But as we will see in a second, when you scale, you cannot always guarantee the order. So this is becoming a very challenging problem you have to tackle. Another very important aspect, not many people are aware of the delivery guarantees. When choosing a queue, you can get at least once, most once, or exactly once delivery guarantees. Obviously, you want exactly once, but again, this is, as we will see in a second, another challenge to tackle. Just laying it out there, this is something to pay attention to. And the two definitions of those terms, concurrency versus parallelism, we always get the feeling that, yes, we know the difference between parallelism and concurrency, but they are very confusing terms in English. We will talk about them through an example in a second. Okay. So phase 3 for us was RabbitMQ. It was, as I said, some kind of an evolutionary growth through those technologies. There was not a clear cut that we finish something and start something new. But we were starting to look into RabbitMQ, which is a very popular queuing platform. It was very, very popular at its peak a few years ago. And what Rabbit will give you as a queue is the fact that subscribers are pulling the data from the queue. So we get messages coming into the queue, and those messages are being pulled by the subscribers. Each one of them is getting a message. When the message is acknowledged as received, the messages are removed from the queue. So what we gain here is the fact that we are pulling the data whenever we can as consumers. It is not being pushed towards our services. We have better delivery guarantees just because of that. We have better fault tolerance. So if a subscriber falls or fails, the messages are kept until it will be turned on again and continue from that point. And we have better concurrency. It means that in this example, we have 3 different subscribers of the same type. They're all nodes, parts of the same cluster, retrieving the data, and only by that, they're distributing the load amongst themselves. So if you get more and more messages coming in, and those subscribers cannot handle the load, you can turn on more and more machines to handle the load. Now, what we're still missing, if you will look at those messages in those 3 subscribers at that exact same point of time, is the fact that we have a racing condition over there. So the race condition is the fact that even if a subscriber started working on a message first, it doesn't mean that it will be processed first. Okay, and it can also fail. So we're missing the ordering just by that design over there. Another issue we should tackle is what happens if we want to keep scaling the queue itself. I mean, the message broker of Rabbit cannot handle enough messages per minute. Yeah, not the subscriber, but the queue itself. So the way it is working in Rabbit, and there's an ability to do that, it's a bit cumbersome, but this is exactly what we've done, is you hook up an exchange. An exchange is a package part of Rabbit, some kind of a load balancer. So publishers are sending data into the exchange, and it effectively working as a load balancer, either splitting the messages among the different queues or cloning. So it can be either parallelism or concurrency. And for each one of the queues, I have concurrent subscribers working on the load. I think the best example to understand is maybe look at what happens in a supermarket queues. So in a supermarket queue, I finished my shopping, and now I need to choose a line. I'm gambling on a line. So there are a few examples. If there are dedicated lines for the dedicated customers, for example, Express line or VIP or something like that, or all the lines are the same. But basically, I'm picking a line and I'm standing in line, and the number of customers that can be processed per time interval per minute is the throughput. Now, what we can say about concurrency is like having an additional help, another guy joining the cashier, helping with packing, etc. It will increase our total throughput of that queue. Another aspect that we've talked about is the delivery guarantee. And the delivery guarantees back at that time that were available in Rabbit is either at most once or at least once. You cannot have exactly once in Rabbit. Now, let's have a minute and talk about that. At most once, meaning we have a producer, we have a subscriber, and we have the queue. Now, the example is going to be the same example, both about the producer and about the subscriber. But let's take the subscriber for a second. So, subscriber pulls the data out of the queue. It can immediately acknowledge that the message was taken, or it can do some kind of a side effect with the data. Now, think about what happens at the exact same moment when the subscriber fails. Okay, and it can be done in the producer as well. Having that the other way around, I mean, first do the side effect and then acknowledge to the queue that the message was taken. What if something bad happens there? So you can either choose to first acknowledge and do the side effect and get at most once, or the other way around and do at least once. Exactly once, or all of nothing, means do everything in a single transaction kind of way, which is quite complex. It means that both the producer, the queue itself should support it, and the consumer all should be idempotent. It means that when you're getting the data, getting the message, you already know that this message was taken as a consumer and disregarded, or have no side effect with it. Okay, so it means you have to implement it yourself as at the application level as the user of the queue. This is something which is very, very important to understand. So the exactly ones is like a whole different separate talk. There's a lot to talk about, and I'm not going to dive into that. I'm just mentioning the fact that it is not supported by RabbitMQ when scaling. Okay, so let's have a quick summary of where we got to at this point of time in the journey. It is complex to scale out. It requires DevOps configuration and overhead, like we saw before. It does not support exactly once, and there are no order guarantees with concurrency. At that point of time, we started looking into Kafka, and this is where our love story started with Kafka. Kafka is actually used as a message bus or an event-driven backbone of an organization. By the way, a quick show of hands, who here is actually working with Kafka in production and writing code against it personally? I mean, not just in the organization? Okay, cool. So most of you do not. I'm not going to really dive into too much details, but I'm going to describe it shortly. So Apache Kafka is like a messaging, but rethought from the ground up. It's a better reason to better reason about it. It's to think about a distributed commit log. So you get an append only kind of journal, and you append the messages that are coming in to the end of the queue at all time. Messages are kept in the queue; they are not being removed. Okay, reads are just a single sequence scan. You have an index. You start reading from your index and keep reading the stream from that point on. This kind of pattern also exists in lots of other technologies like database. You have write-ahead log and commit log in databases as well. So Apache Kafka should be treated as the entire cluster. It's not just a single point of failure machine. So you get a cluster of Kafka machines, and this is how you can scale it. It is distributed by design. Scalable because it's both elastically, transparently can grow and shrink according to your needs, according to your loads. There is no downtime. I mean, the data is being replicated to the other Kafka brokers seamlessly. Data streams are also partitions, and the load is spread across the cluster. It is also durable and fault tolerance because of this paradigm, because of this cluster. Data is both persisted to disk and also persisted to remote replicas. So your data is available both in the master or the leader and these following brokers. Another very important capability of Kafka is that you applicatively as a producer can choose between strong consistency or eventual consistency. I mean, you as a producer can get an acknowledgement from Kafka that the data has been received by all the followers. Obviously, it has an impact on the load, on the performance, because you'll have to wait for that. There is an embedded latency, or you can just say it will be eventual consistent. I'm not worried about it. It is committed in the leader, and that's it. But if one of the servers will fail at that time, this is where you get into troubles if the leg was not already sent to another replica. And the nice thing about it is that Kafka is doing it as a consumer itself. I mean, one broker is actually consuming the traffic from other consumers. So internally, it is working as a queue as well. If we will dive in a little bit into the anatomy of a topic foo in this case, one of the nice things that the guys in Kafka did, and this is the actual innovation, is the concept of partitions into event-driven platforms, very much like you would see in a database. So a topic in Kafka cluster is very much like a table in a database, okay? And the fact that you can partition your tables, you can also partition your topics or tables in Kafka. And because of that, because you have different partitions, if we will look at service A, this is a cluster of publishers that are sending the data into Kafka. It is partitioned, so the load can be handled by a cluster of machines. So the guarantees that you'll have is that the writes are append only per partition. If the publisher want to decide to which partition the data is going to be sent, it is some kind of a hashing function over the number of partitions. But you can specify a specific key. By sending repetitive messages with the same key, different values, to the same partition, the messages will be, the messages order will be kept, but within that partition. Okay, so if you have a multi-tenant environment, like, for example, we have in Wix, a specific website, and we want to keep the messages in order for that website, but we have lots of websites. We're just sending the website URL as a key of that message, and it is guaranteed that it will be sent to the same partition, and the order will be sent. But still, we can scale our capabilities. Another interesting fact is looking at the consumers. The Kafka brings the concept of consumer groups. So if we want to retrieve message or consume messages from Kafka as a subscriber, there's going to be cluster of those consumers. When creating a queue, I need to decide how many partitions I want to have. This is something which cannot be changed once the Kafka topic is created. And the load is being distributed by the different consumers in the group. Another example is another consumer group getting the same messages. I remind you, messages are not being removed from Kafka when they are consumed. The responsibility is upon the consumer group to keep track over the indexes. In service C cluster, I only have one machine. So it just reads round robin from other partitions and keeps track over the indexes from each one of the partitions. So let's try to talk about Kafka versus traditional queues and better explain why eventually we chose to move into Kafka. So the offset is the consumer's responsibility. Messages are kept even if they are consumed up to a retention policy that you define. The pros and cons is more time, but you need more storage on the servers. You get stronger ordering than other traditional queues because of the concept of the partitions. So you can keep order while scaling. You get better concurrency using partitions. So you can have more and more workers working concurrently on the same consumer group. And parallelism is done by different consumer groups. So you're processing the same messages, but for different purposes. And Kafka, and this is very important, guarantees at least once out of the box and exactly once with a bit of applicative work. But basically, it's a paradigm shift in the way we think about event-driven microservices and architecture. It is not just a queue. And it really changed the entire way I'm thinking about async execution and event-driven microservice. And this is the most important thing I wanted to say in this talk. So let's look how it eventually impacted the way we architectured our microservices. So we still have stream of data coming in. We have ELBs, elastic load balancers, that can scale up and down in Amazon. We have the first layer of web servers. What it does, some kind of throttling, basic validation, and just persist the data into Kafka. And Kafka is our persistency layer. Okay, this is our database. If something falls, the data is being kept and replicated within Kafka. The replication, by the way, can even be done across different regions and different DCs altogether. And then you have another layer of your microservices that are actually doing the business logic. And as we can see here, both services A and B are interested in the same data from the same topic. And then you'll see some kind of waterfall or a river or a data flow through your microservices. And this is why this concept is called data pipelines. So we have more and more services getting the data from Kafka and sending the data to another topic in Kafka, doing some kind of business logic, transformation, sanitation, things of that sort. Now, it is not always possible. If, these days, I'm working at Wix, some of our services needs to be processed in a synchronous way. You get a request and you get a response. But, and I'm not talking about latency because we want very good latency, but if you can work in an asynchronous way, get an acknowledge that something has happened, and then receive in a reversed Ajax kind of way, a notification that whatever you requested for did happen, and you can think about it, it will give you a better decoupling over your system. So basically, you're pushing the data in some kind of data sync database of any kind, any sort. And another very important advantage of that is the fact that when you have new product requirements, and in our case, remember that products guys were coming in and saying, guys, we need to have a reporting mechanism over our raw data. We already have Elasticsearch, and we had aggregated data reporting, but we did not store the data for reporting in its raw way. So we were looking for a very quick solution. Time to market wise, we were a young startup, and eventually we came up with Google BigQuery. It doesn't really matter, but it's a hosted DB as a service by Google, can handle lots of load. And what is important is the impact of that on our architecture. And basically what we've done is just created a bunch of servers in a cluster consuming data from already existing queue and just sending replicas of the data over to BigQuery in HTTP request. So you have no risk implying that on your system, and it's kind of future compatible. Okay, unlike monoliths or synchronous execution when you need to do something else in an already existing microservice. Okay, so this point is very important. Lots of people are using microservices these days just because it is cool. But more often, it is more of distributed monoliths. It's small pieces of servers doing lots of things together. Okay, so the right place to split a microservice is to keep it doing just one simple thing. If you're doing another thing, doing it in any decoupled way. So comparing the alternatives, obviously Kafka won. Rabbit had better latency at previous versions of Kafka, so we were still using Rabbit in parallel for specific use cases. But we just switched over Kafka and really enjoyed it. There's a lot of advantages in Kafka these days. It's one of the technologies I like the most that were available in the past few years. Okay, so at this point, I also want to share, as part of the journey, some of our insights working against Kafka in a very large scale, billions and billions of events daily, and kind of design patterns or best practices you get just out of using Kafka. So the first one is back pressure. Think about why we build dams, river dams. Why do we build them? If you get a momentary spike in rains or water coming into the lake on the one hand, you don't want to have a flood on the other hand. You can process up until a certain threshold amount of water on the second hand. So river dam, obviously on top of electricity, has this way to push back the excess amount of water up to a certain threshold. So again, referring back to the reactive manifesto, back pressure allows system to gracefully respond to the load rather than collapse under it. And this is very important. Okay, we're pulling the data is not being pushed. So in our example, we had a new microservice which is sending the data to Google BigQuery, and it is I/O bound. The one processing the data before it was a microservice C, which is CPU bound, doing a bunch of stuff in memory. And when we had issues with BigQuery, it can be network latency, it can be internal problems with BigQuery itself. Service B is being blocked. It cannot process quick enough to what we receive into the queue. So the way it will work like that, it will block also reflect and block service A. Having a queue between them will have that exact back pressure we talked about. So the concept here is the fact that the queue will be longer, what's known as queue lag. Queue lag is a difference between the log size, the number of messages in the queue, and my index, my offset as a consumer, where I'm at. So what we will get is a longer queue, but most importantly is that we will experience no data loss. Nothing is lost. If you remember the example at the beginning that I had a limbo state of a microservice, the data was lost. Another very important impact is the monitoring the bottlenecks. So looking at our cloud, each one of our microservices is monitoring in Graphite, in Grafana. Zooming in, you'll see the obvious CPU, memory usage, GC, things of that sort. But what we also added is us monitoring the lag. As a microservice consuming data from Kafka, if there's a lag, there's a trouble somewhere. Okay, so at the moment I have a spike in lag, I know that something is wrong. And it's very, very easy to spot. I don't care about CPU, I don't care about the memory. As long as there is no lag, everything is okay. Okay, there is no implication for me as an engineer or DevOps guy. Another fact is that we can get the exact resource we need. On a daily basis, you see differences between the amount of data you're processing in different hours of the day, like in spike time or off-rush hours. And if you monitor your auto-scaling group, the sheer volume of your microservices, number of microservices in the cluster, you can be elastic in a way that when you have more load, it will translate to lag. And if you're doing your auto-scaling by the lag, it will just add more machines to the cluster that will help by joining the consumer group and process the data concurrently. It's very important. Another important fact is how we can use this paradigm in tests. As a developer, working on my machine in a small startup company, I have the ability to access production data. Now, without interfering with production data, I can spin a new consumer group and process data in real time, debug it, filter it somehow, put some kind of a breakpoint when something happens, and kind of troubleshoot problems while I'm developing it. While I'm doing QA, staging, while I'm doing test bidding, whatever. It's a very, very easy thing to do. Another aspect which is very important in production is production ops and the way it helps. So I'm going to share a few quick stories. One was a new product requirement that asked us way before the GDPR. There's a finance regulation that requires that the user's data will be kept on EU soil. So unfortunately for us, the databases were in the US and we needed to migrate them. So before you're thinking about ETLs and very complex things to do then, we came up with a simpler approach. We just created a new service, ATUG, which will just throw the data instead to the EU database, to the US database. In parallel, we'll also send the data into the EU servers. And while I can do that in parallel, I'm just waiting for the data to be filled, and then, because we have a retention policy of querying for a month back for our users, we can just wait a month, and the data will be filled. We can compare data in this database and the other, see that we're safe. If there's a problem, we can roll back. And we're kind of risk-free. Another nice thing is time traveling. I mean, if I have a retention of a month in Kafka, I can go back by pointing the consumer group to a month ago and replay all the data and get it immediately in the EU if I want. So it's really, really a nice kind of paradigm shift. Another impact is innovation. We were migrating our microservices from using Python to using a Clojure. The functional paradigm with using streams. As you know, Clojure is a functional programming language in the JVM based on Lisp. Lisp is list processing. It's very, very easy in Clojure to process streams, and this is why we chose that language. And the ability to innovate and replace language was very easy to do by that. So one last thing I want to talk about is low compaction. This is a very nice paradigm. We're using it Wix and Wix code when where I'm working today. I'll first start with a challenge that we needed to tackle. As I showed you before, these days in Wix code we're building a cloud. So we're providing some kind of Lambda functions for website builders, callback that can be put in the backend and be executed in an elastic way on demand for you as customers. By the way, you can register free to create your website and backend code and be currently executed for free in the cloud. And since we are also linked to different verticals in Wix, Wix stores, Wix payments, Wix CRM, invoices like the talk by Lidan yesterday, we are able to be notified at the backend as a message-driven way. So what we can do is execute your Lambda function as in the backend if something bad happens, like a fraud, or there was a price drop and your customers want to know about it, or there's an item back to stock or thing of that sort. So we have our online vertical. We have users that are sending data through Node and putting their configuration somewhere. And in real time, and you see the concept of CQRS because I have an unbalanced situation between writes and reads. I have to read a lot in a low latency, and changes to the configuration by the users, registering to more and more of those events are rarely done. We came up with a nice design, and there's a nice a concept in Kafka which is called low compaction. Low compaction is a different type of queue or a different type of topic. You can set it just by configuration. It will create just a single partition. We also use it with infinite retention, so data is not being deleted ever, so it is kept indefinitely. The head of the log is just a normal Kafka queue, but the secret is being done in the tail. The log is compacted automatically by Kafka. And the way it is done, it is the compacting same keys to have same values. So if you add more and more and more values on the same key, Kafka will compress it and take just the last one. So the data does not explode. If you have an infinite amount of configurable data, it can be a lot, but still it does not explode. Kafka will compact that for you. And because we only keep the last version of the key, you can build an event sourcing machine or a paradigm just on top of that. And this is exactly what we did. We use it as an event sourcing storage. You have a built-in compaction to a key value storage. It's not exactly CQRS, but you can look at it as CQRS. You're decoupling between the commands and the reads. Configuration is sent and stored in the database, and it is being queried in another way. I'll show you in a second. And another challenge was that the subscribers are notified using Kafka consumers in real time versus a database. I'll show you what we ended up with. So the online is sending the data to a database, which is a special type of queue in Kafka. The data is being kept there and being persisted. In my service, in real time, I need to process lots and lots and lots of messages from Kafka, and without going to an external database, when I bootstrap, I read all the data from the queue and keep it in a very optimized way to query. And in this case, when I'm processing the actual real-time traffic, I'm working against local storage in memory. And whenever there's a change in configuration, it is being pushed to my microservice. This is a really cool way to work. So to sum it up, the main takeaways is the fact that event-driven architecture is better decoupling, more resilient, scalable, and give you lots of benefits in production. There's also the engineering and culture impact on the way I'm doing production, on the way I'm doing innovation, because I can decouple different microservices even in different languages. Also available here for open discussion in the Wix booth. We can talk about Kafka usage for low compaction, CQRS, and about Kafka streams. I want to refer to another very important talk that we have today. Do not miss it. By Amitai from Wix, talking about using event sourcing systems by Kafka streams. It's today here in this hall. Some reading material for you guys. Nice reading and videos. And that's about it. So thank you very much.